Professor Peldon. This is Algebra 2, Chapter 6, Section 1. This is part 1 of the video. So exponential functions are now when we're going to put the variable in the exponent. So a times b to the x, so the a is the constant part in front, and b is a constant base. A has to be greater than 0 because anything times 0 will be 0, and the base has to be greater than 1 because if you just kept multiplying by 1, you would get it's the same number over and over again, so it has to be greater than 1, obviously. So the graph down below dictates a common growth of an exponential function. Thus, b is greater than 1. So the domain on this is negative infinity to infinity because it goes forever left and forever right. You can plug it in any x value you want. However, regardless of what you plug in, it's 0 to infinity for the range. You can't get to 0, okay? Because b to any power, no matter what you plug in there, will always give you a number that's greater than 0, because b to the 0 is 1. B to a negative number is just 1 over b to that number. So you're not going to get any negative numbers. You're not going to get 0. If it's decay, b is between 0 and 1. Notice b is not negative. That's a different topic altogether. So 0.23, 2/3, 0.6, 3/5, anything like that are between 0 and 1. So your a times b to the x, right? That b value is between 0 and 1. Can't be 0, can't be 1, obviously. So, and the domain and range does not change. You can go forever left, forever right. Either way, no matter what you plug in for x, you can't get 0 and you can't get negative. So that's our domain and range. Okay, so we're going to do some models. There are 3 basic formulas for exponential models we're going to do in this chapter. This being the very basic one, which does not involve any compounds whatsoever. So throughout the whole chapter, if you don't have any compounds, this would be the formula for you. So this is just a generic one. Okay, so the quantities increase or decrease by a fixed percentage over a time period can be divided by one of the following equations, where r is the percent decrease or increase in t time periods. Sometimes they put just r inside instead of 1 minus or 1 plus, depending on the version of the book you use. Here they use 1 plus or 1 minus. Might just put the amount retained as r on the inside of other books or other videos you might see. In the year 2000, the world population was 6.09 billion. Over the next 13 years, the population increased by 1.18% per year. Determine the exponential model. So if you want to figure out any particular year, and estimate the population in 2005. Okay, so we'll make the model first. All right, so it's y equals the starting amount A is 6.09 billion, and then 1 plus, it says a percent of 1.18, so that's 0.0118, and t is the model. Okay, so if we want to do specific examples, okay, y equals 6.09 times 1.0118, and it says 2005, but you don't want to put in 2005 because that's 2005 years later. That's not what we're doing here. It's from 2000. That's our starting point. You have to have some kind of starting point when you're dealing with time problems. So that is 5 years later. Okay. So at that point, we'll put it in the calculator. We won't get an exact answer, but we'll give it a shot here. All right, calculator. So we get 6.09 times 1 point. Actually, we got to do order of operations here. Exponents first. 1.0118 to the fifth times 6.09. Okay, so we get about 6.45 billion people. Okay, so let's go back And we'll do part B. So part B is when are we going to reach 7 billion people? So 7 equals 6.09 times 1.0118t. At this point, we don't have any method to solve for an exponent that's a variable, so we're going to estimate here. Later in the chapter, we'll learn how to solve in section 6 for that variable. Okay, so we'll just do process elimination here. So 6.09 times the parentheses of 1.0118, and we'll do it to the first power. Not quite enough. So we'll just copy this and we'll keep going. Second, not quite enough. All right, let's try it again. Paste. We'll go to the third power. Not quite enough. So you can see this is growing slowly. So I'm going to skip a few here. Control V. I don't know. How about 12 years? We'll say 12 years. How's that? Oh, looks like that's too much. So let's try 11. So the answer is between 11 and 12 years. Do we know exactly? No. In later sections, we'll determine what it actually is. Okay, so let's go to the student problem. Pause the video, try it for yourself. So how do you read the actual problem? So this is your starting amount called the principal. Okay, so this is $25,000 is the principal amount, which is the starting amount basically, right? The final amount is what the y is, the outcome. And then the 0.85 is the 85% retained. So an equation doesn't tell you what you don't have, it tells you what you do have. So if you only retained 85%, this is a decay of 15%, because you had to have done 1 minus 0.15 to get the 0.85, right? So if you lose 15%, you retained 18%. So this is a decay problem, right? So also that number is less than 1. If you multiply by a number less than 1, you're going to be decay. Okay, let's do some basic graphing. Page 2. Okay, so 2 to the x is our function. So we'll make a standard xy table. -2, -1, 0, 1, 2. So 2 to the -2 is 1 over 2 squared, or 1/4. 2 to the -1 is a half. Anything to the 0 power is 1. 2 to the 1, 2 to the 2 gives us 2 and 4. Okay, so at -2, we're at a quarter. At -1, we're at a half. At 0, we're at 1. At 1, we're at 2. And we're at 2, we're at 4. So our graph kind of looks like this here. So if you read that graph left to right, it is exponential growth. And you can also tell because 2 is greater than 1 in the actual function itself. Okay? All right, so now we want to know domain and range. Domain and range. So as far as the x goes, the input, I can put anything I want for x. So it goes from -infinity to infinity, plus it goes forever left and forever right. However, the range, it only goes down to 0 but up to infinity. Do I get to 0 is the question. No, look at the table. The table goes 1/2, 1/4. So if I kept going in the table, what would the next ones be? 1/8, 1/16, 1/32, 1/64. You never get to 0. You can't get there. I just need parentheses, not brackets. Because we have the invisible line called an asymptote of y equals 0. It's not a very good y. Let me fix that. So this is an asymptotic function, meaning it's approaching a value, but it never gets there. So along that line, the x value changes, but the y value is always 0. Okay, so let's try the next problem. So this is 1/2 x. So make a basic table of values, x and y, -2, -1, 0, 1, 2. All right, so 1/2 to the -2 is 2 over 1 to the 2, or 2 squared over 1 squared, which is simply just 4. 1/2 to the -1 is 2 over 1. Anything to the 0 power is 1. 1/2 to the 1 and 1/2 to the 2 gives us 1/2 and 1/4. So what you notice is we get the basic opposite values of what we had before. Flip the table flipped, basically, is what I should say. I don't know, my pen can't write the 1/4, but oh well. So at -2, we're at 1, 2, 3, 4. -1, we're at 2. 0, we're at 1. 1, we're at a half. And 2, we're at a quarter. There we go. Okay, so basically the graph looks like this. Okay, so reading this left to right on the graph, this is exponential decay. And also you can figure out that 1/2 is less than 1. So therefore that would indicate it's decay anyway, so without doing any of the work of graphing it. So we want the domain and the range. So as far as the input, I can plug in anything I want for x, which is the exponent. It doesn't matter. Go forever left and forever right on the graph for the input. But the range, it goes up forever, but it doesn't get to 0. Same thing here. It's 1/2, 1/4, 1/8, 1/16, and just keeps going if you keep following the table. Because this is asymptotic, it's going towards 0, but never gets past the asymptote, which is y equals 0. Okay, so that is the equation of the asymptote, which will change, but there's 0 here since it's a standard parent function. Pause the video, try these student problems on the next page. Okay, so we'll do a table of values, x and y. -2, -1, 0, 1, 2. So 2/3 to the -2 is 3/2 to the second using the negative exponent rule, which is 3 squared over 2 squared, or 9/4. If we simply just do a -1, it flips it. Anything to the 0 power is 1. 2/3 to the first power, 2/3 to the second power gives me 2/3 and 4/9. Okay, so at -2, I'm at about 2 1/4. And -1, about 1 1/2. I'm at 1. I'm at 2/3. I'm at 4/9. So going down ever so slightly when I read this left to right. So this is exponential. This is the type of function. Decay, which I can tell from the graph, but without doing the graph, you should be able to tell because last time I checked, 2/3 is less than 1. Greater than 0, but that's not important here. Okay, domain and range. It goes forever left and right on the graph. Also, you can plug in anything you want for x. There are no restrictions, so it's all real numbers. X goes to -infinity to infinity. However, the range is 0 to infinity because it cannot go below 0 or even reach 0 because you see how it goes 2/3, then 4/9, then it'll be, 8/27 after that. If I did the next one and it just keeps going, it's never going to reach 0. Okay, let's try the next problem. we'll do an x and y table, x and y. So we have -2, -1, 0, 1, 2. So this is 1.5 to the -2, which is 1 over 1.5 squared, which is 1 over 2.25, which is 0.4 repeating. If you do the same thing with -1, you get 1 over 1.5, which is 0.6 repeating, or 6/10 repeating. 0, anything to the 0 power is 1. 1.5 to the first power is 1.5, and 1.5 to the second power is 2.25. Okay, so approximately 0.4, 0.6, 1, 1.5, 1, 2, 2.25. So it's ever so slightly going up in this case. So this is exponential growth. Okay, you should be able to tell by looking at it also, since 1.5 is clearly greater than 1. Multiply by anything greater than 1, it's going to grow. Okay, so as far as domain and range, I can plug in anything I want for x, so it goes forever, -infinity to infinity. The range, however, 0.6, 0.4 keeps going down, but you never get to 0. So this is 0 to infinity, because you have an asymptote, a line you can't cross, of y equals 0. They tend to put those as dotted lines because it's not visually seen. It's an invisible line you can't cross, so you put a dotted line there. If anything, and that's consistent with trig in calculus. Okay, and as you can think of it as decimals or fractions here, because this is 1 over this, or 1 over this, or 1 over this, and you keep going. So it's always a fraction that keeps getting smaller and smaller and smaller. Hence why it's asymptotic, but you can't get to 0. That is the end of part 1.